Math 1314, Tyler Junior College, Section 4.4, Exponential and Logarithmic Equations. Logarithmic equations, logs and non-logs. Now what do I mean by that? Well, first off, a logarithmic equation is an equation that contains a variable inside the argument of a logarithm, such as log base 3 of 4x minus 1, log base 2 of 1 minus x, log base 2 of 3 minus x. But what do I mean by an equation that has logs and non-logs? It's exactly what it sounds like. Some of the terms are logarithms, and some of the terms are not. In a future video, right around the corner, we'll see how this is different from equations where all terms are logarithms. But let's tackle logs and non-logs. There's a pretty straightforward approach to solving them. We're going to build a technique, or a strategy. As you can tell, it's going to have 4 steps. Let's start with the first one. Log base 3 of log base 3 of 4x minus 1 equals 4. Our goal is to get the x by itself. So every move we do should be geared towards that goal. So what do you think we should do first? There's not much we can do. We can't expand it because the argument is not a product or quotient or a power. Our only option really is to rewrite it in exponential form. That will actually be step 2. Rewrite in exponential form. All that entails is writing down what the answer to the logarithm is doing. Remember, a logarithm is a question. The question this is asking is what power turns 3 into 4x minus 1, and the answer is this power. So 4 is the power that turns the base, 3, into the argument, 4x minus 1. If you can get that chant down, logs become so much easier. The answer to a logarithm is the power that turns the base into the argument. Oh look, we got the x out of the log, and the log's gone. Now we can solve for the x. That's step 3. Finish solving. I guess before we do that, we should evaluate 3 to the 4th power. It's 81. You didn't know your calculator would. Now it's just a simple 2-step linear equation. Add 1 to both sides. Oh, by the way, watch this. I can't tell you how many people I see do that. It's wrong. 81 minus 1 is 80. I don't disagree with that, but you shouldn't be doing 81 minus 1. What should this number be? If you don't know, or if you wrote down 80, that means you need to write down the step that you're doing so that you don't do it incorrectly. Ask yourself, during a test or homework or whatever, what's more important? Saving the 3 seconds it would have taken to written the step, or losing the points for the question because you didn't want to invest the 3 seconds. Sacrificing points for 3 seconds is a horrible trade-off for a student. So if you get arrogant to the point where I don't want to write the step, that takes too much time, and as a consequence you lose points you shouldn't have, well then you get what you deserve. Now don't get me wrong, if you can do the move without writing it down, that's okay. But if you find yourself making those mistakes, stop not writing it. Divide both sides by 4 and we get 82 fourths. It won't divide evenly, but it will reduce to 41 halves. So as a decimal, it would just be 20.5. It's not that bad of a decimal. Ta-da! Wait, there's the 4th step. I know. The 4th step is to check for extraneous solutions. Ah! Another one of those. Yeah. Some types of equations, the procedure just allows extraneous solutions to sneak in sometimes. And I'll explain why this particular procedure does in the next example. But if we check this one, it wouldn't be that bad. If we put the 41 halves here, let's just talk it out. Actually, let's take the 82 fourths and put it back in. Why the unreduced version? Because I'm about to multiply by 4. If we substituted this fraction here, the 4's would cancel, we would get 82. Minus 1 is 81, and the power that turns 3 into 81 is 4. remember? So it works, so it's the solution. It is possible in some equations for the only solution to be extraneous and therefore the equation have no solution. Let's take a look at this one. The main difference is clear. There are 2 logs on the left instead of 1. Our second step requires to rewrite an exponential form, but that's under the assumption that it's in logarithmic form. Log equals a number. This side is not. This is log plus log equals a number. We have 2 logs, so we want 1. Oh, we need to condense. The first step is condense into 1 log. I don't want to write that until we have a reason to, and now we do. The good news is condensing this one is easy. We can just use the product rule, which says the sum of 2 logs is equal to the log of the product of the arguments. So 1 minus x and 3 minus x. So condense, so that we can rewrite an exponential form. What's exponential form for this log equation? Well, 3 is the answer to what question? The question is what power turns 2 into the argument. 3 is the power that turns 2 into this massive argument. Now we're not out of the woods yet. We've simply gotten this out of logarithmic form. But we're solving an equation and we're getting rid of things that are in the way, and the log was in the way and now it's gone. Step 3 is to finish solving. How are we going to finish solving? Well, first off, 2 to the 3rd power is 8. Secondly, this is factored, but the factorization is not only useless, it's in the way. Being factored is good only if you're equal to 0, and I'm not. Since I'm not equal to 0, I don't want this factored. I got to bust this open. In other words, I need to distribute, multiply, or FOIL, whatever you want to call it. The fact that the binomials look backwards is completely irrelevant. Just be very careful and watch your signs. 1 times 3 is 3. 1 times negative x is negative 1x. Negative x times 3 is negative 3x. And here's where people make the mistake. Negative x times negative x, first off, is positive, and then x times x is x squared. So let's do 2 things at once. Let's do 3 things. Number 1, we're going to combine the like terms in the middle. Number 2, we're going to rearrange the terms so the x squared is first. And number 3, we're going to get it equal to 0. Can you do all that at once? Actually, you can if you're very, very, very careful. 8 minus 8 is 0. Now let's start writing it in standard form, general form, excuse me. Highest power first is x squared. Next is my x to the first powers. I have 2 of them that make negative 4x. And then the constant term is 3 minus 8, which is negative 5. Again, it's not really that difficult. You just have to stay focused. Hey, quadratic equation, solve it using the technique of your choice. I'm going to factor this one because it can and I can do it. What 2 numbers add to give negative 4 and multiply to give negative 5? Well, multiplying to give negative 5, it's got to be a 5 and a 1. And they have to be opposite signs. But to get the sum to be negative 4, negative 5 and positive 1. If we set each factor equal to 0, we get x equals 5 and x equals negative 1. Now, here's where a lot of students miss points. I don't feel like doing the last step. I'll just put a box around it and say, these are my answers. Well, if you're in an online homework platform, it's going to go, and it'll probably say something like, check for extraneous solutions. If you're using pencil and paper, your professors, if he or she is merciful, will give you most of the credit because you've done most of the work correctly. If he or she is completely unmerciful, they could go, no credit. And I've seen both ends of the spectrum. This is not over because we have to check for extraneous solutions. And why do we have to do that? Because logarithms have domain issues. Go all the way back to section 4.2. You cannot take logs of negative numbers or 0. You can only take logs of positive numbers. The reason extraneous solutions sneak in is because a solution might cause us to take the log of a negative number or the log of 0. So we have to check for extraneous solutions. Now the good news is, if you know what the issue is, we just need to be on the lookout for that. We can only log positive numbers, so we got to throw away anything that causes us to log a non-positive number. One of these is extraneous. Take a wild guess which one it is, and you're probably wrong. Let's check x equals 5. You can actually do this visually on a problem of this caliber. I'll write it out though. If we substitute 5 into the original equation, we get log base 2 of 1 minus 5 plus log base 2 of 3 minus 5 is equal to 3, and we're asking, are these equal? Hence the question mark over the equal sign. It doesn't take long to realize this is going to come to a screeching halt, because the first log becomes log base 2 of negative 4, and at this point it's over. The other log is also negative, log base 2 of negative 2. Both of these, I don't want to say that they're undefined because they do have an answer. It happens to be complex, but for the purposes of college algebra, we will say that both of these are undefined. That means 5 is bad, it's an extraneous solution, get out of here. A lot of people think, well, the 5 is good and the negative 1 is bad because 5 is positive and negative 1 is negative. But watch this. If we check x equals negative 1, then the first log becomes log base 2 of 1 minus negative 1, which ends up being positive, plus log base 2 of 3 minus negative 1, which also ends up positive. Is this really equal to 3? The first log is log base 2 of 2, plus the second log is log base 2 of 4. And I know the answers to both logs. Log base 2 of 2 is 2. No, it's not. I know the answer to both logs. I missed the first one. Log base 2 of 2 is 1 because that's the power that turns 2 into 2. Log base 2 of 4 is 2 because 2 is the power that turns 2 into 4, and clearly 1 plus 2 is 3. So it is necessary to check for extraneous solutions, especially when you condense, and here's why. Not just because I said so. Condensing only works on a domain that works for every log. What does that mean? There are numbers that I can't put into this log because they make this argument negative, such as 5. 5 made this negative. And there are numbers that I can't put into this log because they make the argument negative, such as 5. But when I condense them, 5 now works. Because 5 gives me negative 4 times negative 2, which is positive 8. When you condense two logs, you kind of mess with their domains in the sense that numbers that may not have worked before might work now. 5 is one of those numbers. This is why we have to check for extraneous solutions. Condensing logs in equations technically changes their domains, and so new numbers might sneak in that didn't work in the original. Check your solutions.